So last week we studied the spherical coordinates Laplace equation, and we focused on a special case with azimuthal symmetry. So in this case, we don't need to worry about the angle phi, and the problem is only consists of the radial part r and another angle theta. So we first solved the radial part. The radial part equation is the general solution for the radial part was ar to the power of l plus b r to the power to the l plus 1. And we also solved the angular part, but we didn't go into steps into how to solve that. I just gave you the solution, and the solution was the Legendre polynomial, and I just claimed that they are the physical solutions that you should be using. So the solution is PL cosine theta, and this PL cosine theta is really special. So these are similar to the Fourier sine series that you have seen before. So for the Fourier sine series, you see in the Cartesian coordinate, if you do an integral of any of these two, and for any of this index n and n prime, it has this very nice relation. So if n equals to n prime, the integration is non-zero, and even though it has a nasty a over 2 constant, and if n is not equal to n prime, so the constant is the integral is 0, and this is called the orthonormal relation. And here you n the set of functions this set of functions will form a basis, even though this basis is not normalized. And it was claimed by mathematicians that you can expand any functions in terms of this basis, and this means that this basis is complete. And now in the angular part, the argument is pretty much the same. So here, this PL cosine theta is also normal to each other, which means here this PL cosine theta also forms a complete set, and if you do integrations, say for L and L prime, and if L equals to L prime, then you simply get the normalization factor. And if L is not equal to L prime, then the integral is exactly 0. So this also normal relation can help us calculate the coefficients, the Cn that we will be using later when we deal with problems. And just like how we calculate the Cn for this Cartesian coordinate basis, for this in this spherical coordinate, we still use the same trick to calculate this coefficient. Now let's take a look at this general solution for this spherical system. That is, we can simply combine the radial part that is here on the left and the angular part on the right. So supposedly on the right there is a normalization factor CL, but since this CL is simply a constant, it can be absorbed into the AL and BL, so we didn't bother to write it down here. And whenever you see a problem with spherical symmetry, then you can actually with asymmetrical symmetry and in a spherical coordinate, you can simply write down your solution like that, and the answer has to be in this kind of form. And the only thing that you want to determine is the coefficient L and the BL. So if you find a way to determine this L and BL, then everything is done. And today I'll give some examples of how to determine this L and BL, and we will go through 3 of them, I guess. So let's check the first one. Now, if you take a look at your basis over here, you can actually see that these bases are actually simple enough. And say that in the problem, you actually find that your boundary condition that you want to match is 1 plus cosine theta. Then, in principle, you have to do this integral. And over PL prime cosine theta, and for many of this L prime, and then that will give you eventually the coefficient, overlap coefficient with the PL prime. I neglected the normalization constant here. There should be a L plus 1 over 2, and now in reality you don't need to actually do this, because you see that this actually involves the calculation of all this L prime, and actually what this does is actually really simply to find out what is this function composed of. So if you simply visually inspect this function, you see that the first term is P0 cosine theta, and the second term is P1 cosine theta. And this means that you don't need to go through all this calculation to integrals to determine this CL prime. The CL prime is actually already written here, and C1 actually should be 1, and C0 also should be 1. And that is so that is the trick of simply not doing the integral, but simply look at your expression to get what's your CL should be, because the CL is simply the asking what's the how many of your function is made of the basis. And now if your function is simple enough, then you can simply compare with your basis and to try to get the answer. So this is the one of the most used ways actually in your either the homework or the exams to calculate the CL prime, because you see that in reality, if you really want to do the integrals, all you have to do this for all of them, and apparently that's time consuming, and if you don't have a computer, you will have to do like endless calculations. So typically there is a cutoff somewhere in your problem, and we will see today that we will dealing with terms such as cosine theta to the cube, and now you can see that this cosine theta to the cube is a polynomial that's limited up to the power of 3. So if you do some trig analysis, you can see that eventually the basis that in your solution should not go above the power of L equals 3. and so you are only going to deal with coefficients of C0, C1, C2, and C3, and you don't need to deal with so the C4, C5, and all above should be 0, and that is simply by looking at your expression over here. Okay, so let's now try to take a look at one of the problem. So here the problem is asking that here the potential is given, and what will be the solution inside this hollow sphere, and so here there is a sphere, and this. Now let me say that there is an angular distribution of the potential on top of this sphere, and the distribution, let's just say it's sine square over 2, and the radius of this sphere is r, and inside is empty, and so there is no charge. Now, what kind of information can we get from this example? Well, first we are interested in the potential inside the sphere, right? So the area of interest should be here, and then there are boundaries of this problem. So one of the boundary is already written here. So there is a certain charge distribution when r equals r, capital R. So is that everything? So can you think of any additional thing that you have to consider? So, by the way, I'll try to copy this expression over here. So in this problem, is this the only boundary condition that you want to consider, or is there any additional things that's hidden in the problem? So anyone want to have a guess, or say, because you see that in the Cartesian coordinates, we typically need to specify 2 boundary conditions, and but here there is only one. But is there any additional boundary condition somewhere? Maybe a way to look at is to simply to look at the expression over here. So this is the general solution to the problem, and yeah, I think you are right. So another boundary condition is when r equals to 0, this v cannot the v must be finite. So if we diverge, then this is problematic. And so here, now let's apply the second boundary condition first. So if we apply this, then this means that this term is gone. So the V is only made of a single term that's in coefficient of AL. And now if we write this down, then so the expression looks much cleaner and simpler right now. So then what you need to do is to apply this boundary condition over here. And this boundary condition will help us determine all this coefficient AL. And then this means that at oh, sorry, I think I missed R to the L. And now if I plug that in, and this should be our specified boundary condition. Now let's try to first brute forcefully calculate this integral. So if we want to get using the Fourier's trick, we simply do this so the Fourier trick is simply to add an additional integral. Now the red part is what you need to pay attention. That is something that we added here. So now this is the identity that we've seen before. So we replace this by the sum of this and of this identity by 2 over L plus 1, which gives us now this way we already pull this AL out of the sum, and the AL is can be expressed as the integral over here. And to determine the obvious AL, we can simply do this integral for all of them. And here, before we actually do this integral, we can make a simplification to this sine theta. Now this sine theta square can be written as 1 minus cosine theta divided by 2, and here the reason that I write like this is because the PL cosine theta are always a polynomial of cosine theta. So if you really want to make use of this Ranger polynomial, you have to re-express your potential in terms of this cosine theta. And now the next step is to okay, so let's go back. So this is simply 1/2 P0 minus P1. So because remember that P naught cosine theta is simply 1, and the P1 cosine theta is cosine theta. There is a process here. So now let's try to in principle, you have to do this using the also normal relation that we get before. So the first one simply gives us this del 0L and a normalization factor of 2, and the second one gives us 2/3 because 2/2L plus 1, and del 1L, and this del 0L is the Kronecker delta that you've learned in your in the what's that, the exercise class in in the first week, I think. So if you go to that week, then I think you should be familiar with that. So the general property of that is del n prime equals 0 if n is not equal to n prime, and equals 1 if n equals to n prime. Let me see, this integral is not over here. Okay, then this means that this AL is actually k/2 when L equals 0, and k/2R when L is 1, and 0 when for other L. And now we can simply we can simply add all this AL and obtain our final solution. So okay, so this one inside the blue box is the our final solution. So you can after you obtain this VR, you can always double check to see if that's correct by checking with your boundary condition earlier. So this is the initial boundary condition, and from here we derive that the what's the potential inside must be in this kind of form. Now,
there's an extra sign layer at the end of the equation, like the last, the green line, the first green line. Why there is an extra sign layer at the end?
oh, because
We didn't have it all the way from. I don't know where did.
oh, sorry. I actually missed the sine theta over here. So if you check the orthonormal relations, here there is a sine theta. This sine theta is simply the line element along with this angle theta. Yeah, sorry, I think I missed this. So there should be a sine theta over here, and a sine theta over here as well. So when we are adding the integral, we should really add not only this one but also this sine theta. Sorry, I think I made a mistake. Okay.
The other question is about the b, the factor. So you said we excluded because when r equals 0, that factor will make sense, right?
Yes.
And when does it make sense?
Okay, so I'll say that. So that's the next problem. So I'll ask you to calculate the potential outside, and so previously in here we calculate the potential inside this shell, right? And now if we want to calculate the potential outside shell, we actually going to make use of this b.
So whenever my domain includes r equals 0, then I can exclude this factor, right?
Yes, otherwise it will diverge. And so now here, let me try to copy this solution. Oh. You mean this one? Yeah. So sorry. I think I was a bit sloppy when I was deriving this adding this integral. So if you check back this orthonormal relation, when we are doing this inner product along this angle theta, there is an additional line element, the sine theta. So if you replace the cosine theta by x, then this orthonormal relation is a bit simpler. But if you do this problem in the theta, then this is the element that you want to take care when you are doing this integral. Okay, so now I just copy the general solution over right here, and then the problem is asking the potential outside. So the boundary condition before at r equals r is still the same. What's that? It's and now because the problem includes the potential at infinity, so another natural boundary condition is when r equals to infinite. So at that point v must be 0, because that's that's the typical reference point that we choose. And now if we apply this condition first to the problem over here, we see that the AL right now doesn't make any sense now, and instead what's making sense is the BL term. So you see that really the AL here is responsible for the potential inside, and the BL is actually responsible for the potential outside. And so here in this problem, we simply ignore this AL, and if we are looking at the potential outside, we actually can simplify our solution to be like this. And now we simply apply the boundary condition again, and after we apply the boundary condition, we can get let me skip some of these steps. So if I the idea is still the same, to apply this additional term PL prime and also the line element, and then doing the integral from del to pi. And in the end, if you work this out, you can see that BL should be k squared over 2 at r when L is 0. So now if we combine this BL coefficient, the final solution should be something like this. And you can double check that the expression over here should actually smoothly connect with the expression over here. Okay, so from this example, then you might get already some experience that actually this AL and BL are really one is responsible for the potential inside, and another is responsible for the potential outside. And once you determine the region of interest, you will choose either one of them. And now the later step is simply identical. Like we all need to plug in the boundary condition at this r equals capital R, and this boundary condition will fix all either the AL or the BL. So in the homework, you will also deal with similar problem, and so my suggestion is that we try to first go through these lectures and keep everything in mind. And when you are doing the homework problem, try to not look up the lecture notes, but try to think through by yourself to see if you can figure out the solutions. So the starting point is always this expression. So you simply memorize this expression, and then fit the boundary condition given in the problem to this function, and then figure out all this ALs and BL. And what's handy is try to have this in your reference book, and try to use this to calculate the coefficient of this CL or AL and BL. Oh, sorry. I think we should have a break. No, we will continue in about 15 minutes.